Good morning, good afternoon, everyone. My name is Dr. Catherine Walsh, and I'm an associate professor and lecturer in the astrophysics group at the University of Leeds. And it's my great pleasure to be the one to tell you all about kind of key findings and current understanding of star and planet formation. So in the first lecture, we're going to focus on star formation, so how stars form from the collapse of molecular clouds that sit in between the stars in the interstellar medium. And then in the second lecture, in the second DARA, we'll go on to talk about how planets form, and also we'll discuss how actually planet formation is a direct consequence of the physics of star formation. So let's get started. So the first thing that's quite nice to do is to have a look at a multi-wavelength image of an active star forming region. And this star forming region, called NGC 602, is actually outside of our galaxy in a neighbouring galaxy called the Small Magellanic Cloud. And you're looking at a composite image here at 3 different wavelengths. So in the purple colour we have X-rays, in the red colour that you see here we have infrared, and then in the orange we have optical wavelength light. And by looking at this star forming region at different wavelengths, you're actually picking up some of the different components of star formation in the star forming region. So if we highlight the X-rays, the X-ray emission is actually coming from very young stars that are accreting material from their surrounding protoplanetary disk that is then getting shocked and is then very bright at short wavelengths. If we look at the infrared, we're actually picking out more the warm dust that's sitting in the molecular material. And this warm dust is telling us where the next stars are going to form. And if we look at the optical wavelength light, then of course we can see the stars that have already formed in this active star forming region. And we can start to also see the edges of the cloud within which we have our molecular dusty material that's glowing with the infrared light, which is the sites of the next generation of stars that will form here. So looking at these different images side by side, you can get a really kind of bird's eye view of star formation. We have our very young stars, we can see in the optical, we have our young stars that are still accreting material, we can see in the X-rays, and then we can see the dense cooler material that's sitting at the edges of the cloud here that's glowing with infrared light, telling us where the next generation of stars will form. So let's focus in on an object that we call a molecular cloud, and this is a very famous object called Barnard 68, and this is an optical wavelength image of this cloud. Now if you were to look at this image, you might think that's a hole on the sky. We don't see any stars, but we see like a very, very busy, quite dense star field around its surroundings. But the image effectively looks black. That might suggest that it's almost like a hole in the sky. But in fact, this is what this is a dense region of the interstellar medium where the density is high enough and the temperature low enough that the material is able to form molecules. And the density is also high enough that the dust that's sitting in the molecular cloud can obscure the light coming from background stars. And the reason that we know that this is a cloud of material sitting in the foreground of the star field that you see here is because when we look at this object in infrared light, then we're actually able to pick that light up with our telescope because the dust grains are less efficient at absorbing infrared light as they are at absorbing optical wavelength light. So you can see that with infrared light, we can start to pick up emission coming from the stars sitting in the background of this molecular cloud. So these objects are of great interest to us because these dense cold regions of the interstellar medium are exactly where the next generation of stars will form. And these molecular clouds and complexes are found all the way throughout galaxies. So this is a nice wide field view towards the center of our Milky Way. And again, this is an optical wavelength light image. And what you can see is the milky light coming from all the stars in our galaxy, but you also see these kind of complex, clumpy filamentary structures that again are clouds of molecular gas and dust that is absorbing the light coming from the background stars. So these molecular clouds are everywhere, and they have lots of different kind of complex morphology. So this is quite a nice example of a molecular cloud complex. It's quite clumpy and structured, where we have these kind of what we call these saccharase globules, where the molecular cloud itself is dispersed, perhaps through stellar winds coming from massive stars, leaving behind only the very densest regions. And again, we expect that in these very dense dark regions, these are where, again, stars will form. And a very nice example of another region which has really been shaped by the presence of massive stars and previous generations of stars is the Eagle Nebula here. So, and the pillars of creation, which we can zoom in on. So what we're looking at again is an optical wavelength light of the Eagle Nebula called M16, and we can zoom into this region here, which are called the pillars of creation. And if we look at them close up with Hubble, the Hubble Space Telescope, you can see that we have these kind of very dense regions of dense dark material, again full of molecular gas, that have been shaped and sculpted by the radiation and winds from the previous generations of stars that have formed in this star forming region. And again, these regions are important because we expect that the next generation of stars will form in them. So let's look at some molecular clouds at different wavelengths. So this is again the Eagle Nebula that we've just visited. So you can see here, so we're going from infrared wavelength, so towards the near infrared with an instrument called IRAC, which was on the Spitzer Space Telescope, up towards the mid-infrared, which was imaged with a different instrument called MIPS. And then you see a composite image here covering 4.5 microns all the way up to about 70 microns. And you can just make out here the pillars of creation that we saw in the optical wavelength image in the previous slide. So why do we look at these clouds at infrared wavelengths? Well, you kind of have a hint from that bird's eye view of star formation that I showed you at the start. So in order to pick up the warm dust that's currently potentially on its way to forming stars, we need to look at that warm dust by its thermal emission, and its thermal emission is going to be brightest at infrared wavelengths. So if you look at the Eagle Nebula at infrared wavelengths, you can see that the image looks very different to the optical wavelength light. Instead of seeing dark regions where the clouds are obscuring the light from background stars, these regions start to become bright, because what we're looking at again is the thermal emission coming from the dust grains sitting in these dense molecular regions. As we go up in wavelengths, we're starting to probe colder and cooler material. So if you look at the Eagle Nebula now at 24 microns, so towards the mid-infrared, you can see that the image again looks very different. So instead of picking up the dust that's sitting in the molecular material at the edges, we're starting to pick up the very cold dust that's kind of sitting in the inner region. And if you look at a composite image from the near to mid-infrared, again, you can see these kinds of different components of dust. The warmer dust within which stars are forming, and the colder dust which has not yet begun to form stars. So everything we've looked at so far has kind of been more towards kind of low mass star forming regions, or at least regions in which massive stars have already formed and they're shaping their surrounding environment, triggering the formation of lower mass stars. But we also have quite in our vicinity massive star forming regions as well. So regions which are actively in the process of not only forming low mass stars, but also forming more massive stars as well. And we tend to set the boundary between low mass and high mass stars. So stars lower than about 2 solar masses are low mass, between 2 and about 10 solar masses are intermediate mass stars, anything higher than about 10 solar masses we consider to be massive stars. So on the right here, you see an optical wavelength image of quite a famous constellation called the Orion constellation, and here we have Orion's belt. This is a famous star called Betelgeuse. And if you see a little fuzzy blob on the bottom here, you can zoom in on that again with a nice big telescope like Hubble, and you get a really wonderful view of the complexity and structure of this high mass star forming region, what we call the Orion Nebula. And you can see that this region looks very busy. There's a lot of energy in the region. There's a lot of structure. You can see dark lanes of, again, molecular gas and dust. You can see kind of holes almost being blasted through the material as well, kind of sculpting these edges and structure in the surrounding material. We can look at star formation in other galaxies as well. So stars don't only just form in the Milky Way, they also form in neighbouring galaxies, and this is an optical wavelength image of the Whirlpool galaxy, one of our closest galaxies to us, M51. And you can see again in this is a composite image. We have the optical wavelength light and also the infrared wavelength light as well. The optical wavelength light is pulling out the stars that have already formed, and the infrared light is showing us where stars are actively forming and warming the dust in their surroundings, which then we can pick up at infrared wavelengths. So here's a composite, again, or a multi-wavelength image of the Whirlpool galaxy, just showing where the current stars have already formed. So that's in the visible or optical wavelength light. In the infrared, especially the near to mid-infrared, we're picking up the warm dust that is actively forming stars. And then at 70 microns, so towards the far infrared, we start to pick up the emission coming from the colder dust that has not yet begun to form stars. And by taking a zoom out of a galaxy in this way, we can actually see in what regions of the galaxy the stars are actually forming. And you can see that the stars are very much forming in the densest regions of the galaxy, which is kind of sitting in the center of these spiral arms in this beautiful spiral galaxy. And we think very much that if we were able to get outside the Milky Way and look at our galaxy, that it would look something very similar to the Whirlpool galaxy, aside from the fact that you've got a little satellite galaxy here that the Whirlpool galaxy is interacting with. So the optical wavelength light is showing us the stars that have already formed. The infrared, in the near to mid-infrared, we're looking at the stars that are in the act of forming and warming the dust in their surroundings. And as we go towards the far infrared, we're looking at the coal dust, which has not yet begun to form stars. So how do we know that stars are forming in these molecular clouds? And again, we exploit the fact that the dust in the clouds obscure light at different wavelengths in different ways. So the dust that's sitting in these molecular clouds within which stars will form are composed of gas, which is about 100 times, there's about 100 times more massive gas than the dust. So it's about 1% of dust that we have in these molecular clouds. And the dust, how the dust interacts with light is a very strong function of wavelengths. So the dust grains are very efficient at absorbing optical wavelength light, but as you increase the wavelength of the light towards the infrared and onwards towards the radio, then the dust becomes less and less efficient at absorbing that light. And so this is why we exploit, again, multi-wavelength observations. It not only allows us to see the different components of the interstellar medium, so the stars in the optical, the warm dust in the near to mid-infrared, and the cold dust in the far infrared, it also allows us to see through the material and actually see what's happening in the inside of these clouds. And that's what you're looking at here. So in the bottom corner of the plot, we're looking at an optical wavelength light, and you can see again, this is starting to look very familiar. This is a Bok globule, which is a kind of small, compact, quite dense molecular cloud. And you can see in the optical, there's a little hint of some emission coming from something kind of sitting inside the cloud. But then when we go to look at this object at infrared wavelengths, and this was done again with the Spitzer Space Telescope, that allows us to see through this cloud because the infrared light can make its way through and escape. And then we see a beautiful image of a protostar, so a star that's just formed, that's generating these jets and outflows that are kind of punching their way through the surrounding molecular material. And you can see again in the optical, one of these jets has actually been able to make its way out of the cloud, and we've been able to pick it up. So these multi-wavelength observations are very important for us to be able to see into the cloud to determine whether or not these clouds already contain already forming stars, such as this one here. So let's now talk a little bit more and focus for the next while on the physics of star formation. So I've shown you kind of an overview of all the different observations that we use to probe the different matter that we have in star forming regions and how we detect, for example, the different components, so the warm and the cold dust. And I've also showed you a little bit about how we use infrared wavelengths to see into the cloud to determine whether or not the clouds are actively forming stars. But in order for a molecular cloud to form a star, there's quite an extreme event needs to happen. So let's take an example of Barnard 68, which you've already seen in this lecture. So Barnard 68 is about 0.1 parsecs in size. So that's of the order of 2 × 10⁴ astronomical units, where an astronomical unit is the distance between the Sun and the Earth. And that translates to about 3 × 10⁻17 centimeters. So we tend to use CGS units in astrophysics a lot. Now, in order for this cloud to collapse to form a star, you can see that the size difference is huge. So we're going from 0.1 parsecs and we're forming a star, a Sun-like star, so it's got a solar radius, a radius the same as the Sun, so 1 solar radii we call that. And that size is about 5 × 10⁻³ astronomical units, which translated to centimeters is 7 × 10⁻10 centimeters. So we can see that this molecular material needs to collapse over many, many orders of magnitude. It's actually between about 6 to 7 orders of magnitude. So that's between a millionth to 10 millionth of its original size. So it's a really huge size range that these clouds need to collapse down to form stars. And because the density goes as the square of the size, so the density increases from 10⁴ per centimeter cubed to about 10⁻26 per centimeter cubed. And that's 22 orders of magnitude. So sorry, the density will go as the size cubed. So we have 6 or 7 orders of magnitude in size change, which translates to about 22 orders of magnitude in density. So again, a really, really huge change in the size and density of the object, going from the fairly, they're still dense, but fairly diffuse molecular cloud all the way down to a star like the Sun. So let's have a little discussion now about the physics that's going on that allows this to happen. So we're not going to go through the full derivation of this today, but we will revisit this in the workshop as well. So let's consider a cloud that is spherically symmetrical, and it maintains equilibrium through the forces of self-gravity and thermal pressure only. So we only have 2 forces that are acting here. We have the force of gravity that's acting inwards, holding the material in the cloud together, and we have the force due to pressure, which is acting outwards and trying to kind of push the cloud apart. That's what we call the thermal pressure force. So this cloud is sitting in a balance. So the inwards force due to gravity is balanced by the outwards force due to thermal pressure. And we can take a thin shell, a thin spherical shell of this cloud that has a width of dr at a radius r away from the center. And this shell of material has a mass of dm of r. So we can kind of write down the balance of these 2 forces. So we have the pressure force acting outwards, which is 4 pi r squared dp of r. So this is the area multiplied by the pressure effectively. And then we have the force due to gravity acting inwards, which you can see here is the gravitational force term, hopefully, that you recognize. So the sphere has a volume, v of r, which can be written in terms of r, so 4 over 3 pi r squared. And we can substitute this into the left-hand side of this expression here, and that gives us a nice differential equation relating the pressure force that's acting on this thin shell of material to the gravitational force helping to keep the shell in place, if you like. So what we do next to this expression is that we integrate the left-hand side with respect to pressure from a pressure of 0 at the center to a pressure of PS at the surface of the sphere, and then we integrate the right-hand side over the mass distribution of the shell from the mass at the center, which is 0, all the way up to the full mass of the cloud, which we call mc. And we won't go through this mass together, but effectively what you end up with is an expression like this here. So we have 3 times the cloud volume, Vc, multiplied by the surface pressure, so the pressure acting on the surface of the cloud, Ps, is equal to 2 times U. U is the total kinetic energy of the cloud, so that's been, because of that integration, we get the total kinetic energy, and then plus omega, where omega is the total gravitational potential energy of the cloud. And again, the reason that these are the total energies is because we've done that integration over that differential equation that we had in the previous slide. So this expression here fundamentally describes a cloud, the physics of a cloud that's sitting in equilibrium, where the pressure force is equally balanced by the gravitational force. And in our derivation, we have only taken into consideration gravity and pressure, but you can modify this expression to include other potential support mechanisms, so things like magnetic fields, which we'll touch upon a little bit later. So we can simplify this expression a little bit further. So, because what we're interested in doing is we're interested in using this equation that again describes the physics, contains the physics that requires these forces to be in balance with each other. We want to use that equation to allow us to derive an expression that we can use to assess the stability or otherwise of a molecular cloud to collapse to form a star. So we can make a few simplifying assumptions. So we can presume that the cloud has a constant density through it. We can presume that the cloud has a constant pressure all the way through it as well. And we can also make the simplifying assumption that there's no external pressure on the cloud. So basically the internal pressure is very much greater than the external pressure coming from the environment within which the cloud sits. And that gives us an even more simple expression where we have 2 times U, 2 times the kinetic energy, plus the total gravitational potential energy equals 0 because we've set the external pressure to 0. And again, this expression here basically encodes all the physics that that sets these 2 forces to be in balance with each other. And we call this equation the Virial equation. Now, we're interested in using the Virial equation that basically describes the balance of force between pressure and gravity. We want to use that equation to allow us to determine the stability of a molecular cloud. So the next thing that we do is we can have a look at these 2 properties, so the kinetic energy U and the gravitational potential energy, and given that for a cloud to be stable those need to be equal to 0, we can then start to look at whenever this equation deviates away from 0. And this is why the Virial equation is very critical for cloud stability. So if 2 times the kinetic energy is equal to minus omega, so we just put the omega on the other side, that means that the cloud is stable, it will not collapse, it's perfectly stable, it will sit there happily, not doing very much of anything. However, if 2 times the kinetic energy is greater than the total gravitational potential energy, then the pressure wins. So the internal pressure force is stronger than the gravitational force, and you get dispersion of the cloud. So the cloud cannot collapse, the cloud will disperse. And then finally, what we're interested in, which is when a cloud collapses to form a star, if 2 times the kinetic energy is less than the total gravitational potential energy, then that means that the force due to gravity wins and the cloud will begin to contract. And this is what needs to happen in order for us to form a star. So we need that the gravitational force is able to overcome the thermal pressure support in order for that cloud to collapse to form a star, and for that collapse to happen again over those 6 or 7 orders of magnitude in size. So what we can do is we can take that Virial equation. We can look at this specific case where we want collapse to happen, where we want pressure to win over the gravitational force holding the cloud together. And we can substitute back in physical properties of the cloud. So these physical properties are things like the cloud mass, the cloud temperature, the cloud density, and the mean molecular weight of the molecules in the cloud as well. And then we can recast that criterion for collapse in terms of mass of the cloud. And when we do that, we derive something that's called the Jeans mass. So in order for a cloud to collapse to form a star, the mass of the cloud must be greater than mj, which we call the Jeans mass, which is equal to 5 times kt, where k is the Boltzmann's constant, t is the cloud temperature, divided by g, which is the gravitational constant, mu, which is the mean molecular weight of the gas, mh, which is the atomic mass unit, all to the power of 3 over 2, multiplied by 3 over 4 pi times rho c, which is this constant density, mass density that we have on our cloud, and this part of the expression is all to the power of a half. So this Jeans mass is the critical mass above which we expect a molecular cloud to collapse to form a star. And in the workshop that we'll do together, not too long after you've watched these lectures, we'll actually revisit this expression and we'll work out a value for the Jeans mass for a typical molecular cloud. And the other thing that we'll start to do is we'll start to look at how the Jeans mass varies with the different variables that we have, different physical values that we have. So the temperature of the cloud, how the Jeans mass then behaves, and also the density of the cloud as well. And the reason that we do that is because when we work out the value for the Jeans mass for a typical molecular cloud, we actually raise a little bit of a problem in that it turns out that it seems to be quite difficult to form stars of the mass of the Sun. But by considering how the Jeans mass varies with density and temperature, we can actually start to figure out how low mass stars form, and we'll also do that in the workshop as well. So far, where have we got to? So we've had a look at star formation on large scales with multi-wavelength observations going from the X-ray all the way to the infrared. But very much when we got down into the nitty-gritty of star formation theory and kind of looking at the physics that's going on as stars form, we were very much focused on a singular object that collapses to form a single star. But as you may have worked out from the images that we've looked at so far, it's not just quite that simple. And it's very rare actually that you get stars forming in isolation. Most stars actually form within large-scale star forming regions, and most stars also form in big ensembles of stars that we call clusters. And this is a really nice video that's about to play here for you that shows like an originally spherical cloud that starts to collapse due to the force of gravity winning over the thermal pressure, keeping the cloud stable. And what you can see here is that, you know, it's not just about spherical collapse. You can see that you start to get a lot of filamentary structure, you start to find these little dense regions where stars are beginning to form and are getting ejected through angular momentum exchange. Here's another little region here where stars are forming. So despite starting off with a nice big spherical cloud of material, the simulations, these hydrodynamic simulations, show that star formation is actually quite complex. And it's not just, you know, this large-scale collapse that happens. You also have the creation of a lot of this interesting, complex structure. And, you know, finally we have here in the center of the simulation a big cluster of stars that have formed. So we started off with something that looked quite spherically symmetric. What we end up is something that looks a lot more complex with a huge amount of structure. So where does this structure come from? So a little clue is kind of given here in this slide. So on the left-hand side, you can see a hot cup of tea, and being poured into the tea, we have some milk. And as the milk is coming into the tea, you can see that it's kind of stirring the tea, it's mixing, and you get swirls and eddies forming as these two different fluids are mixing together. And it's something similar to this nice simulation you see at the top here. We have two streams of material that have slightly different fluid properties, and you can see that as these two streams of material meet and mix, we get kind of eddies forming, and the flow that starts out quite laminar to start with actually ends up incredibly turbulent and complex. And we see this type of structure a lot in astrophysics. So you kind of get a sense of it in the hydrodynamic simulation that you saw, also in the observations that I've shown you so far. But we also have this turbulence, if you like, present in atmospheres as well. And this is a really nice image of the atmosphere of Jupiter, where you can see again these kind of eddies and turbulent mixing going on in Jupiter's atmosphere. So what's happening is turbulence. So here's a large-scale view of the Carina Nebula. This is quite an interesting region. There's a massive star over here, which ejects towards the end of its life at a Carina. And what it's doing is it's kind of, because it's towards the end of its life, it's ejecting a lot of its external material out into the surrounding interstellar medium. And it's doing that through winds, stellar winds, and also through radiation as well. And this imparts a huge amount of energy into the surrounding medium. And this is what's kind of injecting energy and turbulence into the star-forming region, and what's creating these kind of beautiful structures, creating these filamentary structures, and also leaving behind these dense regions here, very similar to, again, the pillars of creation that we saw with when we looked at the Eagle Nebula a few slides ago. So this is kind of what we call feedback. So large massive stars, as they go through their lives and towards the end of their lives, inject a huge amount of energy into the surrounding medium, and they kind of stir up the molecular gas and dust, and they create all this interesting complex filamentary structure and also blow away material, leaving behind these very dense regions within which, again, we hope that stars will form in the future. So, you know, when we look at these nebula, so these clouds of gas and dust in star-forming regions, you know, the gas really looks very much like the tea. So what we're looking at is a turbulent medium. And we know it's turbulent because when we take spectroscopic observations of these regions, we can see that the gas is actually moving faster than it should for the temperature that it's at. And the reason for that is because the gas is turbulent, and the turbulence has been injected by these energetic stars. So these massive stars blow out stellar winds, so these are energetic particles that impart energy into the surrounding medium. When these massive stars die, they go supernova, that sends shock waves through, injecting a lot of energy again. But you can also inject turbulence into a medium through collisions with other clouds. And certainly we know that not everything in space is sitting static. Everything is interacting, and sometimes these clouds can come together. And then the mixing that you get, similar to the milk and the tea, stirs up the material, creating turbulence, showing imparting energy into the gas that then is moving faster than it should. So how do we know that the gas is turbulent? So I hinted at the fact that we use spectroscopic lines. So a lot of what I've shown you so far has been mainly looking at emission coming from either stars at optical wavelength light or from dust at infrared wavelength light. But what we can do is we can also look at these environments with telescopes that are equipped with spectrometers that are able to have a fine enough spectral resolution to see individual lines of molecules and atoms. So atoms we tend to trace at a kind of UV visible wavelengths, but we can look at molecules at infrared to submillimeter wavelengths. So if we take a typical molecular cloud, it has a temperature of about 10 Kelvin, so they are very cold, and it's got a mean molecular weight of 2.4. And this is because the cloud is mainly made out of molecular hydrogen, which is atomic weight of 2, and about 10% of helium, which is an atomic weight of 4. So that's what leads to this mu of 2.4. And the molecules that are sitting in the gas in these molecular clouds are moving. Even though it's very cold, they're still moving, and they're moving with a velocity distribution that creates Doppler shifting that leads to not just a emission at a single frequency, but emission over a range of frequencies. And the velocity width of this range of frequencies, if you like, over which these molecules are emitting, can be estimated by the sound speed in the gas, which is Cs, and that's equal to the square root of kT. So K is Boltzmann's constant times the temperature divided by mu mh, where mu is this mean molecular weight, mh is the atomic mass unit. So we're looking at molecules that are moving with slightly different velocities along the line of sight, and then that the light that they emit is Doppler shifted because of their slightly different velocities. And what this velocity distribution leads to is an emission line which is Gaussian shaped. It has a dispersion, so kind of a width on the order of 0.1 kilometers per second. And another property that we measure directly from these molecular lines, so the full width half maximum, is about 2.3 times the dispersion. So we're actually going to come back to this expression and work out the typical velocity of molecules in a molecular cloud in the workshop. So this expression basically tells us what we should expect. And what was expected actually isn't what was found when people went to do spectroscopic observations of molecular clouds. So what you're looking at here is work done back in the 1980s, this has been known for a long time, where there was many observations of molecular lines made towards lots of different star-forming regions. So each of these letters indicates an object in a particular star-forming region. And what this person Larson did at the time was measured this full width half maximum from the spectral line. So you can see here this is a Gaussian. So we have the full width at half of the maximum of the line. And he worked out the velocity dispersion, which is related to the full width at half maximum with this expression here. He plotted that value, the log of that value, on the y-axis here versus the size of the cloud in parsecs. So we're going from about 0.1 parsecs down here all the way up to 100 parsecs at the far right of the x-axis. And you can see that if you plot the velocity dispersion versus the size of the cloud, that this increases with size of the cloud. And this was not expected. So there seems to be something in the physics, something in the scale of the turbulence that's going on that seems to suggest that the velocity dispersion gets bigger the bigger the cloud is. Or conversely, the smaller the cloud, the lower the velocity dispersion you would measure in the cloud. So Larson did this for a huge number of clouds at a variety of distances, scales, resolutions, sizes, and he persistently found that when he looked at the total width, so the total width that you measure with your spectrometer and the telescope, that squared, has got two different components. It's got the thermal component, which is what we looked at a couple of slides ago, and it's got this non-thermal component as well. And the addition of those two terms squared gives us the total line width squared. And what Larson found, as you might have guessed from the previous slide, is that for many clouds, this non-thermal component is dominating often by a factor of 10 or even more over the thermal line width of the cloud. And as we consider successively smaller cloud, this velocity then approaches the ambient thermal velocity. So what this is telling us is that these clouds are turbulent because there's some source of energy that seems to be, that's acting on many different scales, that is leading to the gas moving faster than we expect it to be for its temperature, that then is leading to these larger than expected line widths. So we know that the gas is turbulent because when we measure the line width is much bigger than what we expect from thermal motions alone. So this is very good evidence that many of these molecular clouds are turbulent medium. So let us come back to something that I hinted at a few slides ago, and that's the origin of jets and outflows. So this is a really nice image. Again, you can see a dark molecular cloud, an optical wavelength image. So we have our dark molecular cloud here. In the center, we have a forming star. And you can see that punching out of the bit of the cloud that's coming, that's facing us, you see this kind of beautiful optical jet that's created this shocked bow shock region outside in the surrounding medium. So this is very strong evidence that there's a forming star sitting in the center of this molecular cloud. And if we look at this image at longer wavelengths, so remember at longer wavelengths we can start to see through the cloud because the light can escape. The dust is not as efficient as absorbing the light. Then what we start to pick up is that we don't just have these jets that are generated by forming stars, we also have these what we call outflows. And what the submillimeter image is showing you here, you can kind of start to pick up some of the coal dust that's sitting at the edge of the cloud, but you also see this kind of very structured outflow where again the submillimeter emission is kind of tracing the outflow cavity edge. So these jets are generated by young stars, they punch through the surrounding medium and they kind of stir up and impart momentum to the surrounding medium that creates these kind of very structured outflows as well. So in order for, these are really good ways for identifying the fact that we do have a star actively forming in the center of this molecular cloud. So where do these jets come from? This is a little video that hopefully illustrates this quite nicely for you. Oh, the video didn't play. Why didn't it play? There we go. So we have a molecular cloud. We have a dense region forming, so about here. You can see we had a shock wave that helped gravity overcome thermal pressure. So this object is rotating. It's collapsing over many orders of magnitude. So what the object does is it flattens out, very much like, a pizza dough if you were to spin it as you're making a pizza. But that object's also dragging in all of the magnetic field lines that are present in the cloud as well. And as the object is rotating and spinning up and flattening out, it's dragging those magnetic field lines with it. They're getting twisted up. And that is what we think is actually helping to generate these very highly collimated jets that then, again, impart momentum to the surrounding molecular material, creating these outflows. So we can see these jets very clearly. So I showed you an example of one coming out of a molecular cloud. where again, when we looked at longer wavelengths, we could see the outflow cavity very clearly. But we can also look at these jets just coming from isolated sources as well, so sources that aren't embedded in molecular clouds. And this is quite a interesting object called HH30, so Herbig-Haro 30. And you can not only see the jet very clearly at optical wavelengths, you can see how it's also changing over the timeline between 1995 and 2000. So these are objects that are changing on our time scale, which is quite unusual for astronomy. But you can also see kind of this interesting bow-like structure, kind of above and below this dark lane. And what we're actually seeing here indirectly is the presence of that flattened rotating structure, what we call the disk, that is formed again from the collapse of the cloud. The star itself we cannot see. We can only see the presence of the disk by the fact that we don't see the starlight. So the disk is kind of indirectly detected here because it's sitting in the plane of our line of sight and it's absorbing the light coming from the star. But we can see scattering of the starlight coming from the top side and also from the bottom side of the disk. So we can indirectly see the presence of a disk through this scattered light image and the fact that we have this dark lane that's obscuring the star as we're looking at it edge on. So these optical jets have quite interesting properties. They're very shocked ionized gas, so they're very bright in things like H-alpha and ionized ionic lines, like this is sulfur 2. They have quite a low ionization fraction, about 10%. And as you can see, they're very highly collimated, so their length is about 100 times greater than their width, which is what this ratio means. They're also quite dense, and they're also very, very fast. And that's why as these jets impart onto the surrounding interstellar medium, they create these beautiful bow shocks, and they actually also excite atoms and molecules. Actually, they can dissociate molecules as well, creating excited atoms that emit light quite strongly at optical wavelengths as well. That's what we call these knots. And they're so fast that they are supersonic, which is why they create shocks. And you can estimate the radius at which the jets are launched by considering the expression for the escape velocity, and we're actually going to do that in the workshop. Herbig-Haro 30 is actually quite a good example of quite a collimated jet, but some of these objects also have some evidence of precession. So going like this, meaning that they have kind of a wiggly jet, and you actually saw that in the embedded object that I showed you a few slides ago. So not only do we see these optical jets, we can also clearly detect the molecular outflow that they also drag along with them as they punch through the surrounding medium. And these molecular outflows, you can see, look very different to the jets. So what you're looking at here is emission coming from this object here in the CO line, and this is a rotational transition of the carbon monoxide molecule. So it's quite a low energy transition, so we're looking at cold gas. And the outflows are not quite as fast as the jets. They're between 10 and 50 kilometers per second, but that's still sufficiently fast to create shocks, especially along the outflow cavity edges. Because we're looking at the spectroscopic line, we can also look at the Doppler shifting on the line that tells us something about the morphology of the mission that we're looking at. So in the northern lobe here, the outflow is red shifted, and in the southern lobe here, it's blue shifted. So this object is pointing away from us in the north, so the emission coming from here is going away from us, and in the bottom here the emission is coming towards us. So we can kind of also constrain the morphology of the object through how red and blue shifted the lobes are. You see this bipolar outflow. You can see that they're usually poorly collimated, so they're about twice as long as they are wide, but they do extend much further out into the interstellar medium than the optical jets. So of the order of between 1 and 3 parsecs. And they actually do carry away a huge amount of mass. So between 0.1 and about 100 solar masses can be contained in these outflows, depending on, of course, the size of the object that you're forming in the center. So these jets and outflows are playing a very important role in actually helping to stabilize the formation of the star. So as you bring together, because you're collapsing over 6 or 7 orders of magnitude, and you have a little bit of angular momentum at the start, so a little bit of rotation, when that object collapses, everything spins up very, very fast. And if you've no way to actually carry away angular momentum, the star would never be able to form, because it would be spinning so fast, it would spin itself apart. So these jets and outflows play a very important role in carrying away angular momentum from the system, allowing the star to slow down and actually stabilize and form. So that's why they're very important, not only as markers of star formation activity, but also in actually helping the process of star formation itself. Another way that we can kind of see, especially very embedded forming stars, is we can actually exploit observations at radio wavelengths as well, and we can see the very, very dense ionized gas that is forming at the base of the jet. So that's what you're looking at here. So you have this is a map of the radio jet from a young forming star at 3.6 centimeters. The star is here, and the contours show you the strength of the emission. So the denser the contours, the stronger the emission. The more diffuse the contours, the weaker the emission. And these allow really unique view into especially very dense star forming regions, because radio wavelength light is able to fully escape the cloud. It's not attenuated by dust, it's not affected by dust. So if we really want to see forming stars within very dense star forming regions, radio wavelengths is a really good way to exploit that, and we can detect this emission coming from the jet. So the origin of the emission is actually free continuum emission, and this originates when you have a positive charge, and you have something like an electron that's being deflected by this positive charge. That's a change in energy, and that change in energy creates the emission of a photon at quite low energy. So this is why it's at quite long wavelengths. And these jets are usually less than about an arc-second long, and they're aligned with the outflow axis as well. But again, a really powerful way to actually see evidence of forming stars, especially in very obscured, very dense star-forming regions. So just to kind of have we now have a kind of a bit of a picture of the different components that we have of a forming star. We have a cloud that gets pushed beyond the Virial stability criterion. Gravity wins, begins to collapse that cloud. The cloud conserves angular momentum, so it starts to spin up. It creates a rotating flattened structure, and the system generates jets and outflows to help to carry away angular momentum to allow the star to stabilize and form. So if we zoom in, we have a protostar forming here. We have a flattened rotating structure we call a circumstellar disk. That's surrounded by a circumstellar envelope that's still collapsing and feeding the star. And then we have our blue shifted and a red shifted jet that is created by the twisting of the magnetic fields. If we take a zoom out, we can see that not only do we have this jet, we also have these molecular outflows that extend much further out into the surrounding molecular cloud and medium. And we can also see on larger scales these what we call knots, which are kind of the bow shocks created by the impact of the jet on the surrounding medium. So you can see that a forming star creates a lot of structures, and the energy imparted also by the star creates a lot of visible structures quite far away from where the star is, such as these outflows and knots. So just to finish, we'll just do a little recap of what we covered in this very, very fast-paced overview of star formation. So the first thing that we did was we looked at multi-wavelength observations, and we showed how these multi-wavelength observations reveal the presence of young stars. That's through X-ray emission, because young stars are actually very bright in X-rays, and we'll explain why that is the case in the next lecture. But also the different components of star forming regions as well. So we can use infrared light to see both the warm dust, which is actively forming stars, and we can use longer wavelength light to see the colder dust, which is where the next generation of stars will form. We then also started to consider the different physics that generates that goes into forming a star. The main forces that we considered were the force of gravity acting inwards, and the support mechanism of thermal pressure, which is acting outwards and trying to disperse the cloud. And in order for stars to be able to form from these large structures, we really need gravity to win and gravity to be the dominant force, allowing collapse to happen. We then briefly just covered the Virial equation, which sets the stability criterion of a cloud, which has support through thermal pressure only. And we also use the Virial equation to derive the Jeans mass, which sets a mass threshold above which we expect gravity to win and a molecular cloud to be able to form. And together these two equations kind of encode the stability criteria of molecular clouds. We also went on to kind of have a more broader kind of look at star formation. So in our theory that we looked at, we were kind of looking at individual objects, but most stars form in kind of big clusters and quite complex environments. And when we took a zoomed out view, we could see that a lot of these star forming regions that we're looking at seem to have a lot of energy, a lot of structure, and a lot of complexity. And that is because the medium within which stars are forming is turbulent. And that turbulence is injected through energetic processes like massive stars that drive a stellar wind, supernova, which are massive stars that have ended their life, that create shock waves through gas. And also you can get turbulence injected in a local sense just through the jets and outflows that are generated by forming stars as well. We then went on to have a look at, touched upon a little bit on angular momentum conservation. So when these clouds collapse to form stars, they naturally form a flattened rotating structure through angular momentum conservation. And as we'll go on to talk about in the second lecture, this is very important, this is what we call the protoplanetary disk. So if angular momentum were fully conserved and nothing changed and the system stayed spherical, then the star would not be able to form because it would be spinning so fast it would spin itself apart. So by spreading out the mass over a larger area, by getting rid of mass through jets and outflows, that allows the star to stabilize and to form and to not spin itself apart. And as I said, these jets and outflows, that was the last thing that we looked at, very important for taking away mass and angular momentum, but they also can inject energy and stir up the surrounding material as well. So that's just a little summary of what we covered in lecture 1. In the next lecture, we'll move on to discuss how planets form around young stars, and in particular, we're going to very much focus on this object here, what we call the protoplanetary disk. And I'll see you there in the next lecture.